Hello everyone, I hope you are doing well. In this video, we are going to solve problem 6 from chapter 7 of Introduction to Statistical Mechanics by Roger Bowley. So let's see what the problem statement says and then we'll dive into the solution directly. So here's the problem statement. As you can see here, according to the theory of relativity, the energy E of a particle of rest mass m and momentum p equals h cut k is given by this expression E square equals p square c square plus m square c4. This is the energy expression for a relativistic particle. Okay, and in part A, what is the density of states in energy of a relativistic particle? We need to find out the density of states formula in terms of energy. Okay, where we are given this expression, this approximation for us, that is p square is very much greater than m square c square. Okay, so we can use this approximation while solving our expression for density of states. So what is the density of states in energy of a relativistic particle enclosed in a volume V? So in part A, we simply have to find out the density of states in terms of energy using this approximation, while in part B, we are told to find out that given expression for the partition function of an ideal gas of n relativistic particles at high temperature. So we have to find out the partition function of an ideal gas which has n particles, okay, which is enclosed in a volume V at a very high temperature T, and they are capital N in number. So keeping all this information in mind, we have to solve our question 6 from chapter 7 of the book I mentioned before. So let's start with the solution. So we are given with this expression for energy. This is the relativistic formula for the energy, for the total energy of a relativistic particle of mass m and momentum p, where we are further given that p equals h cut k. All right, and we can use that approximation which is given to us under approximation that p square c square is very much greater than m square c square. Okay, we can reduce this formula into a simple expression. Let's see what that expression would be. We can take p square c square as common. Okay, and after taking it common, taking common means dividing it with all of the quantities that are inside that bracket, which are these two. Okay, and when we divide it with p square c square and with these, so it's 1 that is left behind, and here we are left with p square c square. Okay, and as we can see that p square c square is very large than m square c square, so the denominator is very large quantity and numerator is a very small quantity. Then we can approximate that if the denominator is very large, than numerator, then we can take their ratio, which is m square c4 p square c square approximately equals 0 or negligible, we can say. So the formula reduces to p square c square 1 plus 0. Okay, you can use these equivalent sign that we have approximated it, and hence we are left with this, and E taking under root on both sides is PC as a result. And if you put the value of P right here, which is h cut k, then it's h cut kc. Here k is the wave vector and it's different from the Boltzmann constant, which will denote by kb, k with b in subscription, to show that they are different and in order to avoid mixing them. So it's E equals h cut kc, which is the approximated energy of a relativistic particle whose p square c square term is very large than its rest mass term. Okay, now let's jump into the part where we are finding out the density of states. This is one of the important step to do. Okay, because we'll put that value of energy into our density of states formula expression to solve it, and we should know what the expressions we'll be using. So the formula for density of states in 3D, because we can see that they have told us that the particles are enclosed in a volume V. So density of states in 3D is given by this expression in terms of energy specifically, because we want to find the expression in terms of energy. Okay, that is why I'm using this formula. Here we can see this is the wave vector. 2 pi square V is the volume in which the gas or particles or whatever it is enclosed. This is the differential of K with respect to energy, and let's say this is equation number 1. Now we know that from, let's say this is expression number 1 and this is expression number 2. So now from 1 we have E equals h cut kc. So taking differential of both side, differentiating both sides with respect to k, so it's this. Okay, here h cut and c are constant quantities, so they will come out of the differential operator and it will be applied on k alone, and differential of k with respect to k is 1, and we are left with this. Since we want to put the value of dk by de, rather de by dk, so we'll simply inverse this quantity. So since de by dk is equals to h cut c, so dk by de would be equals to 1 over h cut c. Alright, let's say this is expression number 3. Now insert this expression right into expression number 2 to find out the expression, final expression for density of states. So 1 over h cut c and v k square 2 pi square h cut c. Since we want to find out the density of states formula in terms of energy, so here we have to make some substitutions to express this term in terms of E rather K. Okay, so K variable has to be removed, and for this we'll make that substitution in which we'll put E equals h cut kc. Here K would be equals to, if you take h cut c onto other side of equation, we are left with this. So this is the value of K in terms of E. We will put that value right into this expression because that's something that we wanted at first place. Now we wanted to express density of states formula. We want to find out density of state formula in terms of energy, so it should be in terms of energy. Taking squares, it's E square divided by 2 pi square h cut c, and it will be h cut square c square because the square is on the whole thing. So 2 pi square h cut cube and c cube. This is the density of states formula for the energy of a relativistic particle, where we had this approximation in our mind and we use that approximation. Okay, so this is the answer for part A. Now let's do the part B. In part B, they have told us to find out the partition function for a ideal gas of n quantity enclosed in a volume V at very high temperature. So part B, we need to find out the partition function. So we know that the partition function is given by following expression in terms of density of states. It's 0 to infinity integral that runs over d of k dk e to the power minus e of k by kb d. Okay, here this is d of k, which is density of states in k variable. okay, not in E variable. So we'll use the density of states expression in terms of K variable for an ideal gas. dk is simply the differential, and e to the power minus E of k. E of k means energy term or expression that has been expressed in terms of K variable. Okay, we'll simply plug that value of E right into this equation, okay, divided by kt. Here d of k is the density of states in K space, and simply from equation number 2, the formula that I have mentioned here, this term is d of k, okay, and you simply have to put k square by 2 pi square here, and in E we'll use this formula. Okay, so by using this formula we'll get partition function for a single ideal relativistic gas. Okay, for n number of gases we'll do some other thing onto that formula and we'll get it. So let's say let's first find out the partition function for a single molecule of an ideal gas, and we will do the rest of the process at the end, which is very short process. So let's do that. It's very simple, but it requires some integration, and just that, if you know how to integrate, then it's super easy. Let's put these values. Vk square over 2 pi square. Here k is the wave vector, it's not Boltzmann constant. For Boltzmann constant we'll use k with the subscript b. Okay, and here it is E of k, which is h cut kc by kbt. Okay, now we have to solve this integration. Let's do that. Here we can see the integration runs on the k variable, so all of the other quantities which could be taken out of the integral should be taken out of the integral. First, it's v by 2 pi square. These are the constant quantities, and we'll take them out of the integral, and rest of all these values, k square dk, and even this expression has k in it, so we cannot put them outside the integral. And z is equals to v by 2 pi square 0 to infinity k square e to the power minus h cut c by kbt. These are constant quantities into k, which is wave vector. I'm just writing them separately. Okay, now let's solve this integral. It's 2 pi square, and limits run from 0 to infinity. Keep that in mind. Now let's use integration by parts, in which we'll use this expression as first term and this expression is second term. Okay, I hope you know how to integrate by parts. The formula is very easy. Let me mention our formula. It's, let's say we have first term here and there is a second term here, and we are integrating it with respect to some variable x, and integration by parts will work like that. We write, sorry, it's like we write the first term as it is, okay, then we integrate the second term with respect to this, okay, the negative sign, then integral again, and we derivate the first term with respect to that variable, okay, dot integration of second term again, and this whole result that we obtained is integrated again with respect to x. Okay, so what you do is you find out this term first, this term first, and then you integrate it again, negative sign, you integrate it, multiply by the first term as it is, and this is very simple. Let us apply it here, and it will be very easy if you practice it enough times. So here k square is the first term, k square as it is, integrating this second term h cut c k by kbt with respect to k, and minus derivative of k square with respect to k dot integration of e to the power minus h square c k by kbt dk. Okay, and this whole quantity again integrated with respect to dk, and keep that in mind, we have the limits of integration here. So what you do is to, this is the bracket, main bracket that I have started, and this is the end point of that bracket, and we write 0 to infinity here. Okay, we'll solve it. All of these things will be solved first. We'll calculate it first, and we'll apply the limits of integration at the end. All right, so v by 2 pi square and k square, this is simply the integration of e to the power minus x dx. The same formulas apply here, because we can see the variable, which is the main variable, which is k, is to the power 1 here. Here is a single k, it's not k square, it's not k cube or else. Okay, that is why I have compared it with this term. So its integration is super easy. It's like e to the power minus x divided by the derivative of power. Okay, so the power is different here from that case, so we'll apply accordingly. It's e to the power minus h cut c k by kbt. This formula only applies when we have x to the power 1 here. Okay, it's not applicable when we have x square here, for example. The method becomes different. So we'll divide it with the derivative of power. Power here is minus h square c k by kbt. All right, and negative sign again. This integration is little bit lengthy, and derivative of k square is simply 2k. Then we have integration of this term, which is again this term, so we'll write it simply the same thing. Is h c k by k b t dk. Limit of integration 0 to infinity. V by 2 pi square k square e to the power minus h c k by kbt divided by, now here the derivative is with respect to k, so it will be only applied on k terms. Here we have single k, all of the other terms are taken as constant, so they will be taken out of the bracket. So h cut c by kbt is taken out of the bracket, and it will be applied on k alone, and this is equals to 1, simply dk by dk. That is why this is something that we are left with. I'm taking 2 out of the integral here. It's k right here, e to the power minus h cut c k by kbt divided by, here the derivative would be same because the terms were same, and dk 0 to infinity. All right, so v by 2 pi squared k squared e to the power minus h cut c k by kbt divided by minus h cut c by kbt. This negative and negative sign becomes positive, so 2 kbt, this one jumps into the numerator. Okay, h cut c, and it is this. Now still we have one more integration here, as we can see, that needs to be solved before we are putting the you know that integration, that this should be solved first, and let us do that. Again, we'll use the integration by parts formula here, because it's So I think I should solve it separately. Let us call this quantity as I1. Okay, let me calculate it separately and I'll put it right into this expression. Let's say this is expression number 4 maybe. Yes, let's say it's expression number 4, and let us calculate E1 separately, because otherwise it would be it will become very confusing, and since there are some lengthy terms involved here, so it's a better idea to solve them separately. I have supposed this integral to be equal to I1 alone. Okay, this one thing, the constant term, is just a separate thing. Here we go. Now let us solve this integral. Let us take k as the first term and this one as the second term, and using the integration by parts technique, first time as it is, integrating the second term. These things will repeat, we know this, the integration of this term, as we have done it before, so we can directly put these values right into this. Okay, so derivative of first term was k, so k here, and dk dk. Okay, so k, and the integration of this term is simply this, as we know. Okay, and minus dk by dk is 1, and integration of this term is this, h gets c by kt, and we'll integrate it again. H gets c by kbt, these are constant quantities, so they'll come out of the integral, and this is k, this is kbt. Okay, keep that in mind. It can minus h gets c k by kbt minus h gets c by kbt minus this minus and minus becomes plus, so it's kbt by h gets c. I hope you know the fact that it's something like let's say it's a in numerator and it's b by c in denominator, so we can write it as a divided by b by c also. So if we change that division sign into multiplication sign, that's the basic rule of division, we invert this fraction, so it's c by b, and we have c as kbt here, that is why I wrote it in numerator and b in denominator simply. So that's how it's done, and again we have this integral. Okay, and integration of this integral is again the one that we did before, so I'm writing directly what we are about to get. It's this. Okay, and we have this in numerator, so it becomes kb square t square, and h cut square c square, and this negative sign makes it negative here. Hence this is the result of I1. Since all of the integrations are solved, this dk gets eliminated. Now we'll insert that value right into equation number 4. All right, and we'll put the limits of integration, and after putting the limits of integration we'll get the result. Sometimes the calculation becomes so lengthy that I tend to avoid some steps, but I think the space is not enough here. Let me write it somewhere else. Here it is. that is the value of I1. And after putting the limit of integration, most of these expressions become 0, and I will tell you the rule. Okay, because putting all of these limits of integration will become such a hectic thing. This whole thing is multiplied by both of these quantities, so I'll write this thing with this and with this as well separately. Negative and 2kbt by h get c into this whole quantity c k by kbt. Okay, limits of integration from 0 to infinity. Since this quantity is common to I1, this quantity will appear with this term and with this term as well. That is why I have directly written this term with both of these quantities right here, okay, to avoid an extra step. Now you can see here that this is the single term in which we have an exponential alone, okay, with k variable in it. There is no k variable in these terms that are being multiplied with it. There is a k variable only in the exponential term. Besides that, here we have this k variable here and also in the exponential, and here as well we can see here is a k square and k appears in the exponential as well. So while we put the values, maybe I should put them because maybe some of you get confused. So when you will put the upper limit, which is infinity, you will put it right into the exponential, because exponential tends to get to 0 way before the k approaches to infinity. It's thing, a fact about exponentials, it's their property that they vary very fastly. So as the k becomes very large, this quantity becomes 0 well before k approaches infinity. So this whole quantity becomes 0 when we put infinity as limit in it, okay, as k approaches to infinity. This is something that you know how we deal with this. I hope you people are understanding it. Here 0 and infinity are the values of k that needs to be inserted here. It's something like upper limit inserted into this expression minus low limit into this expression, okay, and we'll do it over all these expressions. So when we put infinity into these expressions of exponentials with negative sign in them, okay, it becomes a case like negative sign with infinity in place of k. So it's e to the power minus infinity. We can write it as 1 over e to the power infinity, and e to the power infinity is infinity, and 1 over infinity is 0. So these quantities, all these quantities become 0 when we put infinity in them, okay. And when we put 0, it's like here we have k. When we put 0 here, k is equals to 0, so this whole quantity becomes 0 when we put the low limit. This whole quantity becomes 0 as well when we put k is equals to 0, because k is multiplied with all of these quantities. But here we'll get a non-zero result only for this term. We'll get a non-zero result because there is no k that can make it this whole quantity equals to 0. So this quantity is only the non-zero term that will be left with. So that is why I'm writing this thing directly, in which we'll put 0 in exponential, and we'll see what result we'll get. It's like k is 0, so the whole quantity becomes 0, e to the power 0, and e to the power 0 is 1. This negative sign gets cancelled out when we use this formula, like upper limit minus low limit. So it's minus from formula of low limit, and the low limit was negative already. That is why negative and negative becomes positive. That is how I have done it. So it's 2 kb cube t cube by h cut cube c cube. Okay, this 2 into gets cancelled out and we are left with v by pi square kb cube t cube by h cut c. We can write it as this. Okay, this is the partition function of an ideal gas. Okay, and you can do another thing by, in some books we have h in place of h cut, so you can simply put h by 2 pi here. Okay, and you can simplify and get some other result, other forms of result. For example, if you put this thing right here, you can get 8 pi v by into kt by hc whole cube. Okay, if you use this expression right here, okay, simplifying it gives you this formula. So these are the two different formulas for the partition function of a single ideal gas, which is relativistic. Okay, now since we have ideal gas of n relativistic particles enclosed in a volume V, so there is an additional step that we have to do in order to find out the final partition function, which is z to the power n divided by n factorial. Since we have capital N number of ideal gas molecules, so we'll simply put the value of z here. 1 over n factorial remains as it is. We have 8 pi v kt by 8c whole cube and a whole power n. Okay, or you can put whole power n into this on this formula as well. So this is the partition function of an ideal gas of n molecules enclosed in container of volume V at extreme conditions. Energy of an ideal gas is of an ideal relativistic gas is approximately equals to Vc. That's how we take the extreme conditions into account, and that is the partition function that we needed to calculate.